All right, we're going to talk about our periodic trends, and we're going to always kind of keep in mind this concept of the valence electrons. That's what we're looking at for our periodic trends. How are those elements going to interact? The main periodic trend, if there is one that you remember, you need to remember the effective nuclear charge. Okay, we give it the symbol of Z for the symbol of our atomic number, our protons, and then EFF for the effective nuclear charge. So it's the effective charge that the protons in the nucleus are acting on our electrons. This is by far the most important periodic trend that we're going to talk about. It actually dictates almost all of the other trends. So our effective nuclear charge is essentially the amount of positive charge that our electrons are feeling, they're experiencing, they're being attracted to. So I put felt in quotations, just that's a little too touchy-feely, but it's the best way to describe what effective nuclear charge is. It's the pull, it's the hold that the nucleus has on the electron. Okay, it's how tightly is that relationship, how tight is that relationship? How strong is the attraction that's being experienced by the electron from those protons? Okay, we use Z effective. We also have ENC is also a shorthand for it. Before we start talking about the trend of effective nuclear charge, we have to understand what shielding is. And shielding is what occurs when we have multiple layers of electrons. Okay, so if you think of our energy levels, so n equals 1, n equals 2, n equals 3, if we have electrons that are in those outer shells, we still have those inner shells that exist. And those inner shells also contain electrons. So what happens with shieldings is that the inner electrons, so the electrons that are not the valence electrons, they actually almost shield the outer electrons from feeling that positive charge from the nucleus. Okay, now the outermost electrons do feel some charge because otherwise they wouldn't stick around, they wouldn't stay on that atom, but they don't feel the complete charge of each proton that's in the nucleus because the inner electrons kind of they block that charge from getting out to those outermost electrons. So the outermost electrons are going to be easier to manipulate because they don't feel this great effective nuclear charge. So in shielding, our inner electrons block some of that positive charge so that our valence electrons, the ones on the outermost energy level, they're not going to be held as tight. They're pulled in less by the protons in the nucleus. So our trend for effective nuclear charge, as we go from left to right on the periodic table, that effective nuclear charge, or Z effective, is going to increase. So as we go from left to right, effective nuclear charge increases. And that's because as we go from left to right, and when we go left to right, we're just thinking about one period. Okay? So we're comparing going from left to right, all in the same period. Okay? All of these electrons are in the same level, so they're all in n equals 2 level, at quantum level. But what happens as we go from left to right is we increase the number of protons in the nucleus. So if we increase the number of protons in the nucleus, we're increasing the ability for a positive charge. So effective nuclear charge increases. So essentially we have more positive charge. I am going to try and color code my notes. So left to right trends will be in blue, top to bottom, so in a group will be in green. So as we go down a column, and again, you're sticking to just one column, you're not zigzagging across the periodic table. As we go down, okay, your book is a little misleading on how it describes this. Effective nuclear charge doesn't increase, even though we're increasing the number of protons. What happens as we go down is our quantum level, our n value, increases, which means our electrons are getting further and further away from our nucleus, so shielding becomes a bigger issue. So our effective nuclear charge actually increases going up the periodic table. So moving up, effective nuclear charge increases, and that's because as we move up the periodic table, our quantum level decreases, so our electrons are closer to the nucleus. All right, so remember, this is the trend to remember. This is going to dictate most of our periodic trends. In fact, it's going to affect our atomic radius here. Atomic radius is defined as the distance from the nucleus to the outermost electrons. As we move actually from right to left, this is going to have an increasing atomic radius. So atomic radius increases. And this is because as we move from right to left, our effective nuclear charge decreases. Okay? So if our effective nuclear charge decreases, what's happening is our electrons aren't pulled in as close, okay, because they're not feeling as much positive charge, so those electrons kind of are able to get further and further away. As we move down the periodic table, atomic radius increases. And that's because as you move down the periodic table, your quantum level increases, your n value increases, which means your electrons are further away from the nucleus. All right. Last trend to talk about is talking about our ionic radius. So what happens when we form ions? And we have a couple different trends to look at. Okay, the first trend that we're going to look at is comparing a cation to an anion. And then we'll look at comparing the charges of a cation versus the charges of an anion. So ionic radius is just the level of, or the radius of our ion. So just like atomic radius, except we're losing or gaining an electron. And we want to just focus on what's called the representative elements. So this here represents your group B. Okay, and we're going to ignore group B, just like we did in chapter 3. Okay, group B elements have their d orbitals, and it's much more complicated with d orbitals because they have different quantum levels from the other ones. So here you're in your 4s, here you're in 3d. So it gets more complicated. It's not as simplistic of a picture. So we just want to focus on group A elements, and these are called the representative elements. So we have 1A, 2A, and then essentially over here we have, what is this, 5A, 6A, 7A. Excuse me. So comparing a cation to an anion. Excuse me. For a cation, if we look at, say, sodium, okay, sodium wants to lose one electron. So sodium, we had looked at the first video, has the electron configuration of neon, and then it has 3s1. For the sodium ion, okay, it's going to lose that outermost electron. So it's going to have an electron configuration that's identical to neon. And if we look at a periodic table, sodium is in group 3, or excuse me, in period 3. And when it drops down to neon, it drops a quantum level. The outermost electrons drop that outermost level. So the outermost electrons are now in n equals 2. Okay, so that corresponds to when it loses the electron, its ionic radius is going to decrease. And that's because your outermost electrons are in a lower quantum level or lower energy level. For our anions, if we look at, say, fluorine, the element fluorine is going to be just like helium, plus it'll have 2s2, 2p5. When it forms the fluoride ion, it's actually going to be just like neon. What happens is it has to add an electron. So rather than looking at it this way, if we were, say, to draw out its energy levels. So we have N equals 1, N equals 2. For fluorine, there are 9 electrons, so 2 electrons in the N equals 1 level. Then an N equals 2 has 7, so we have 1, 2, 3, 4, 5, 6, 7. When it adds an electron to form the fluoride ion, and we still have the same electrons in that center, but now we have 8 electrons in this outermost level. So we've increased the number of electrons without affecting the number of protons, because we're still looking at fluorine as the atom. So we still have 9 protons in that nucleus. So by adding an electron, these electrons now have to compete for the attraction of the same number of protons. Okay, so that competition basically is what's causing more shielding. These electrons are now repelling each other. So that's going to allow this the ionic radius to be a little bit bigger, because these electrons are now shielding each other. They're starting to kind of push each other away because they're not feeling as strong of a pull from the nucleus. Okay, so for our ion or anions, okay, the ionic radius is going to increase because you have more electrons, which results in more shielding. Okay, so they're feeling less pull from the same number of protons. Excuse me. So if we look at now ions of multiple charges, so if we look at a -1 anion versus a -2 anion versus a -3 anion, so if we look at -1 versus -2 versus -3, as we add more and more electrons, we have more and more shielding, so our ionic radius should get larger as the negative charge gets larger. Okay. So -1, say, is going to be this big, -2 is going to be larger, -3 is even larger because we have more shielding. And we have the same charge, we're just adding more electrons, so we have more shielding. If we look at cations, okay, a +1 versus a +2 versus a +3, this is actually going to have the opposite size effect. Rather than increasing with the increasing numerical value of the charge, or the magnitude of the charge, our size is actually going to decrease because we're taking away the electrons. So the electrons that are left don't have as much competition for that effective nuclear charge, the positive charge that's felt. So a +1 cation is going to be larger than a +2 cation, which is going to be larger than a +3 cation. And this is because the electrons that remain experience a higher effective nuclear charge. Now, we can't compare, say, the size of a +3 ion versus a -3. Okay, we don't want to compare numerical charge of a positive to a numerical charge of a negative. We don't want to do that. If we're going to compare an anion to a cation, we want to look at this relationship. Okay, so these trends are only within a series or a set of, say, cations, or a series or set of anions. And when in doubt, the atomic radius trend is going to win overall.